Thank you.
Yes, hello everybody. My name is Hamaad Shah. I work at Deutsche Bank as a lead data scientist there. So today, just the topic is quite. I find it quite interesting in trying to use generative models for something like estimating value at risk. So generally, when we talk about variation autoencoders or GANs, we tend to think of images or some other sort of similar sort of data sets. And so I thought it would be nice to kind of explore whether we can do the same for finance data, let's say in terms of, let's say, calculating the value at risk. So this work of mine, just a disclaimer, is doesn't necessarily represent anything I've done in the past, with my employers or anything like that. Just to put it out there. So so basically, the topic we'll be discussing today is we will be looking at GANs for market risk management, and the one thing I really admire about GANs is that they implicitly allow us to maximize the likelihood of potentially very complex distributions, and then if you can do that properly, then you can perhaps generate very valid samples from such a distribution. So so dealing with high dimensional data, as we all know in this room, is something we come across in finance as a very key component. So GANs potentially can allow us to model such data and take some, let's say, valid samples from that, rather than relying on something like multidimensional Gaussian distribution. So just a brief, I'm sure I don't have to go through this, but just a brief point, a couple of points on VAR. So VAR essentially is just a measure of portfolio risk. It kind of allows us to figure out what sort of capital we need, against a potential event that could, let's say, destroy the bank, essentially. So so essentially, the estimation of VAR is very important to be able to figure out how much capital we need, the capital to, let's say, debt ratio that we should potentially have. Because capital funding is very expensive. You cannot fund all your assets in the bank by your capital. There's just a portion of that is funded by the capital, and the rest is obviously levered up by debt. So the estimation of VAR is very important, as you might be aware. So again, just a very simple data set that I just took across. I didn't have any, let's say, particular choice in, let's say, any. I just took some data set from some prices around Apple, Google, Microsoft, Intel, and Box, and try to calculate their continuous compounded returns. And so in the first instance, what we'll be doing is just, as you might all be aware, that we'll be looking at three major methods of market risk management for the estimation of VAR. Essentially, the variance covariance method, the historical simulation method, and the Monte Carlo simulation method. So there are many other ways, more complex ways, and there are obviously more coherent ways as well, conditional value at risk, especially shortfall. So, but we won't be going into that. It's just a, let's say, in a sense, a show and tell to see whether we can actually use GANs for VAR, essentially. So. Again, just to recap on what I just mentioned earlier, so variance covariance method, essentially, we are trying to figure out in a very straightforward manner what our tail risk is. Non-parametric methods is essentially some sort of bootstrapping based on historical data, and Monte Carlo methods essentially are kind of more important for some securities you might have that might have, let's say, path dependency, so to speak. So for some areas that might be a bit more useful. So I just chose these three basic, let's say, very standard workhorse methods that we use in market risk management to basically show that, hey, can we actually do the same with GANs, essentially. So this is the distribution of the stock portfolio that we're holding. I just assume that we're holding an equally weighted portfolio. It's nothing too complex. Obviously, you can try to figure out which weight vector you need to hold to be able to, let's say, optimize some value that you might be interested in, part of which could be VAR. So these are the 1% VAR values that we have here based on the three different methods. And now we will delve into, let's see how we can use GANs for adding that fourth row there to figure out whether that can give us a sane estimation of value at risk here. So essentially, the purpose of deep learning is to learn a good representation of high dimensional and noisy data. So it has had good success in discriminative models, let's say the PY given X and so on and so forth. But generative modeling is perhaps fared worse because of the limitations of explicit maximum likelihood estimation. So in most cases, as we might imagine, we might not exactly know what the distribution is of that complex data set. So being able to implicitly maximize the likelihood without knowing what the likelihood should be is a very useful feature of the GAN. And we can also, just as a side note, we can use the features learned by the discriminator, which we'll get to at the moment, as a feature engineering tool for your representation learning, so to speak. But that's just a side note. So there are two main components to a GAN. So the generator and discriminator. So and they play an adversarial game against each other. So the idea is that the generator tries to generate realistic synthetic samples from noise, and while the discriminator learns how to figure out whether this is a real sample or this is a synthetic sample. So just to get those concepts across a bit, bit more concretely. So you have two components, two neural networks, two deep learners, so to speak. So you can see the parameterized by theta g and theta d there. So the generator basically takes noise and gives you a synthetic sample, and hopefully that will be more realistic. And what the discriminator does is tries to figure out, hey, given a sample, whether real or synthetic, is it real or synthetic? So the idea is that if the generator can create more synthetic samples that are more realistic, it can actually fool the discriminator in a good way. So basically, the GAN simultaneously tries to train the discriminator and the generator, in that it tries to, let's say, discriminator needs to correctly classify between real and synthetic samples, while the generator tries to create synthetic samples that the discriminator incorrectly classifies. So if you look at the simple objective function there, it's just a minimax game based on the discriminator's objective function. And as I just said earlier, so the discriminator tries to maximize it, and the generator tries to minimize it, given the parameters they have been allowed, essentially. So basically, the game has set up that we're trying to obtain a solution, theta d for d, such that it maximizes that value function, which is just the discriminator's value function, objective function, and simultaneously we're trying to obtain a solution theta g for g, such that it minimizes that function itself. So we do not simultaneously train the discriminator generator together. We train them step by step by, let's say, training discriminator for a few steps, freezing it, and then training the generator. And we repeat this process for a couple of steps here. So the optimal solution, essentially, as you can imagine, is that if your synthetic distribution and your real distribution is fairly similar, you should get that PGX is equal to P theta x, essentially. So let's just go through a few steps to show that is theoretically indeed the case here. So let's start off with the optimal discriminator. So let's try to find that, and we'll try to expand the terms there and just focus on that term that I just mentioned there, the jdx given theta d here. So let's focus on that and try to find the optimal discriminator. So with a few steps, you can get to that point. And if you actually remember equal to p theta x, you will notice that the optimal discriminator should be half, which intuitively makes sense if basically you have reached an optimum, an equilibrium, so to speak, and the generator is creating a realistic enough sample, then the discriminator will not be able to figure out whether it's real or not, so to speak. So that from an intuitive point of view as well, that makes sense that the discriminator will end up start to just outputting half values, essentially. So given the optimal discriminator, then we try to work with the generator's generator side of the game, essentially. So that's essentially the same objective function, but obviously with the discriminator's optimal values now plugged in. I won't go too much in detail, just for the sake of time as well, but essentially this kind of emphasizes the fact that we're playing a two-model game. Two players are playing an adversarial game against each other, and it's very important to realize this to actually figure out why GANs work, and theoretically from a theoretical point of view. And that obviously is very important to be able to use GANs in practice for something like market risk management. So a few basic points. I won't go too much into that around lambda divergences and Jensen-Shannon divergences, but they're important to, let's say, prove this point, that the GANs, the generator's objective function is basically, I won't go through all of that, it will be available later, but all these steps essentially lead to the last point there, which essentially is that the minimum value is obtained when the p theta x is equal to pgx there, as you can see there. That's where the Jensen-Shannon divergence just basically vanishes, and that's essentially the global minimum, essentially, that we need to go to. So just to emphasize that point again, it's the objective function generator the global minimum value is attained at minus log 4, which occurs when the following holds, and we've proven that above. And obviously that intuitively makes sense that when that happens, then basically you basically reach some sort of equilibrium, and your synthetic distribution is fantastically similar to your real distribution here. So let's Now let's apply to the data set that we saw earlier. So you might remember the actual distribution we saw earlier. So this the green parts that you see, the density value there, essentially is an untrained GAN. So I'm using a bidirectional GAN, but it's essentially there are many flavors of GANs, but it's for this purpose I just went slightly differently. But the idea is essentially the same. So you can see with the untrained GAN, it's not remarkably similar at all to the distribution we are trying to, let's say, mimic or be able to take realistic samples from. So and this is an important point. So once we train it for a while, then you can see that the trained GAN essentially is outputting the distribution that it outputs is actually remarkably similar to the actual distribution that we saw there. So I'm just going to end mine now. So right, so we're right at the end here. So this is the fourth row that I was talking to you guys about. So so just to end on this note, so we can see that we can use GANs for essentially as a competitor to the existing solutions that we have. And the reason I find it quite useful is because we don't quite need to specify or use, let's say, something like a copula or something of that nature to be able to generate valid distribution, valid samples from a very complex returns distribution. So essentially that's the end of my my little talk. And I just thought it interesting to apply GANs to or generative models to this area of market risk and finance. So yeah, that's just, thank you.